So we've spent some time talking about if a series converges, sometimes we can find the exact sum of the series. So far we've seen that we can do so when we have a geometric series or when we have a telescoping series. However, sometimes we'll have the information that a series converges, but we won't know the value to which it converges. The next best thing is that perhaps we can approximate that value in a way such that we have a good idea about how good our approximation is. This leads to the idea of finding the error in an approximation and hopefully being able to bound that error. To start off with, before we start getting into the specifics of error, let's define a way of thinking about error. So to give this some context, we're going to assume we have a series that is known to converge, and let's say the sum of this series is capital S, but we don't know what S is. Then we can use the nth partial sum, which we've defined as S sub n, the sum of the first n terms of the series, to approximate the value of S. If this is what we're going to use as an approximation, then we can define the error, which I'll use the notation capital E for error, subscript n is indicating how many terms we're adding together to approximate the sum. And so I'm going to define the error as capital S, which is the sum of the series, minus S sub n, which is our approximation of the sum. If we think about what that really represents, we can simplify that a little bit. So in particular, capital S is the sum of all of the terms. So we could write that as A1 plus A2 plus through A sub n plus A sub n plus 1. And then there's really no stopping because that goes all the way to infinity. If I subtract the sum of the first n terms, we would write this similar process, but we know that we would end at A sub n. So by writing it like this, we can see that there will be a lot of things that cancel. In particular, everything is going to cancel up through A sub n. What we're left with starts at A sub n plus 1 and then continues until infinity. So what we can see here is that we can actually express the error itself as an infinite sum. If we're using the nth partial sum to approximate this series, the resulting error can be the sum from k equals n plus 1 to infinity of the terms a sub k. So this is one way to interpret the error here. And I want to emphasize the relationship between n, which is how many terms we're using to approximate the series, and the fact that our sum here starts at n plus 1. And again, if you look at the work we've done right above this, we can see that that's because we're canceling off everything before n plus 1, the terms from 1 to n. The first term that has not canceled is that a sub n plus 1, and everything after remains. So one thing we'll come back to a little bit later is the way we're defining error here. We take the true value of the sum and we subtract the approximate value. And the other thing to keep in mind is that because we're assuming we can always find for a specific value of n, the nth partial sum, if you're able to exactly find the value of s, the sum of the series, then you should be able to exactly find the value of the error by taking that known sum and subtracting the partial sum. So let's see this in practice. Like I said, we're a little bit limited in our examples where we can actually find the sum, but consider this one here, the sum from k equals 1 to infinity of e to the minus k. Well, here we can find our error in a number of ways, but I'll point out that first of all, what I want to look at is the 10. That's telling me the value of n. So this is asking us to find e sub 10, which is the true sum of the series, minus the 10th partial sum. What we have in this example is a geometric series. So notice we can express e to the minus k as 1 over e to the k. So that makes it a little bit more clear that it is geometric, and I can see what the value of r is. And we're subtracting the sum from 1 to 10 of the very same terms there. Because this is geometric, we can find these explicitly. So this one here is an infinite sum. The first term is 1 over e, and we're dividing by 1 minus r. We also have a finite sum formula for geometric series. Again, the first term is 1 over e. This has the same denominator, but we're going to put in the numerator 1 minus r raised to the number of terms, which is 10. Now we could simplify this a little bit. And what I want to point out is perhaps an easier way to find this error is to use how we've defined it as the sum from n plus 1 to infinity, which is, of course, in this case, 11. Because that's an infinite geometric sum, we can just jump right to our infinite geometric sum formula. We have we have 1 minus r in the bottom, and the first term here is 1 over e to 11. We would get that up here because you could cancel the 1 over e in this numerator with the 1 over e here. Multiplying 1 over e by 1 over e to the 10th, we sure enough get 1 over e to the 11th. So we get the same answer in two different ways here. The first one is maybe a little bit more explicit that this is a difference, but I can take advantage likewise of the fact that we can express e sub 10 itself as an infinite sum and compute that. But either way, I was able to find the exact error. Another situation in which we can do this is when we have a telescoping sum, because we can find the exact value of the sum there. So the one I have here is actually one that we went over in our sequences in series lecture. So I'm going to build off of some of that pre-work. So previously, we found that s sub n is equal to 1 minus 1 over n plus 1. And the way we did that was by listing out partial sums until we observed a pattern. So using this knowledge, notice first of all here, n is 8. So we're asked to find e sub 8, which is s minus s sub 8. Now if I have the nth partial sum as I do here, s is going to equal the limit as n approaches infinity of s sub n. So to be clear, this is the sum of the series. Minus, for s sub 8, I'm going to plug in 8 for n. So evaluating this, my limit here approaches 1. And we have this here. The ones are going to cancel, and distributing that negative sign, we end up with 1/9. So again, we're able to exactly compute the error. But what I want to stress the importance of here is that in both of these cases, we had to rely on the fact that we could find the true value of capital S, the sum of the infinite series. In most situations, once we've established that a series converges, we don't have the ability to find the true value of S. So this is kind of leading to what we're going to cover next in relation to error, is in those instances, we can't find the exact value of the error, but we're going to develop some ways that we can bound that error. And of course, if you want to have a good estimate, you'd like your error to be small. So in some instances, we'll have both an upper and a lower bound, but really the upper bound is what's significant because we'd like to make sure that our approximation is good by ensuring that our error in our approximation is not too large.